Thank you. Well, you've heard about solar radio astronomy in the frequency range of thousands of megahertz from Ken Tapping. And today I would like to tell you a little bit about solar radio astronomy at much lower frequencies, in particular the observation of solar radio bursts. And these observations were made by Ted Hartz of the Defense Research Telecommunications Establishment, DRTE. What we see here is a dynamic spectrogram of typical solar radio bursts. These are made from ground-based arrays, and the dynamic spectrogram, as you see, is a display of the intensity of the bursts versus frequency on the left-hand scale and time. And you can see that some bursts, like the type 2 burst in the middle, the frequency drifts from high frequency to low frequencies, high is at the bottom, during the burst. And the same thing, here we are, happens with the type 3 burst over here on the left, except that the frequency drift is very much more rapid. I'm going to be just talking about type 3 bursts today. The type 3 bursts are believed to be due to energetic electrons which are emitted in bursts from the sun and travel outwards through the solar corona plasma, generating plasma waves as they go at the characteristic frequency, plasma frequency, which depends directly on the density of the surrounding corona. Oh yes, and I knew I wanted to say something else. And as these electrons, which I will call exciter electrons because they excite the plasma waves, move out through the corona to lesser and lesser densities, the frequency of the plasma waves and the radio bursts both decrease, and that's what causes the frequency drift effect that you can see. This is the dynamic spectrum of a single type 3 burst. Here, the high frequencies are at the top of the scale, and you can see that the frequency drifts from high to low during the burst. I think I skipped one there. That looks better. Now, Hertz observed the solar radio bursts with the Alouette satellites, which were designed by DRTE in Ottawa to probe the Earth's ionosphere. As you know, I'm sure, the Earth's ionosphere has a great effect on radio propagation because the ionization in the ionosphere refracts radio waves. The Alouette satellites were not only intended to probe the ionosphere, but determine the structure of the ionosphere, really electron density versus height. And the structure of the ionosphere is normally determined with the aid of variable frequency radars, which are called ionosondes because they sound the ionosphere. And ionosonde at the ground level can determine the structure of the bottom, we might say the bottom half of the ionosphere, and to determine the electron density of the upper part of the ionosphere requires satellites like the Alouette satellites, which contain their own ionosondes. Now this is the ionosonde, like most radars, requires an automatic gain control in the receiver, or AGC as it's called. And what the AGC does is reduce the gain of the receiver when the signal received is very strong. And this effectively compresses the range of signal strengths that the receiver can handle. If we look at the high frequency, let me explain. This is, the caption explains it. This is the record of the automatic gain control voltage as the frequency of the receiver scans from a half a megahertz to about 12 megahertz. And if you look at the high frequency part of the AGC voltage, you see it's spiky. That's due to radio signals from the ground, which penetrate the ionosphere. But you can see that below the penetration frequency, the variation of the AGC voltage and the background noise level that's producing it varies rather smoothly. I can't show you how smooth it is because my hand is too shaky. But anyway, you can the dashed trace there shows a typical scan through the frequency spectrum, and just incidentally, Hartz used those to determine the frequencies, low frequency spectrum of galactic radio noise. Hartz noticed that sometimes the background noise was enhanced considerably, like here, to this solid trace, and that the enhancement, the frequency range of the enhancement increased toward the low frequencies from one scan to the next. It extended further into the low frequency range. And that enabled him to immediately recognize that these enhancements were type 3 solar radio bursts because of this frequency drift effect. And this is shown now better in this is a succession of scans of the type, the Alouette 1 satellite. Each scan takes about 18 seconds. And you can see that the energy of the burst moves from high frequencies to low frequencies on successive scans. This is another representation of just the same sort of data. And except here is we see the intensity of the burst at a fixed frequency. And here we see it at a number of frequencies ranging from 8 megahertz down to 2 megahertz. And you can see the peak of the burst moves to later and later times. And this is just what you would expect, because if it's produced by electrons moving out through the corona into less and less dense regions, the burst produced will be lower and lower frequency. You can see also, if you look at especially the burst down at 2 megahertz, that the decay time is longer than the rise time. And the decay is due to two phenomena. One is velocity dispersion of the electrons in the exciter stream. Naturally, the slower electrons would be producing the tail of the burst. And another effect is the decay of the plasma waves themselves, which are producing the burst. And this decay or damping of the plasma waves is due to electron-ion collisions in the solar corona. Now this slide shows these two components or effects in the burst separated out, or as mathematicians would say, deconvolved. The A part of the slide shows the profile of a typical type 3 radio burst in this wavelength range. And the B part shows that as a superposition of decaying plasma waves, which are initiated at various times due to velocity dispersion in the exciter stream. And the C part just shows the excitation of the burst, which reflects the velocity distribution of the exciter electrons. The D part shows you the decay of plasma waves produced at any particular frequency. And it's exponential and represented by the standard formula. Anybody who's done any electrical work would know, e to the minus t over tau, where t is the time and tau is the decay time of the burst. And it's tau, the decay time, or the damping rate, which is of principal interest here, because the decay time is due to the decay of the plasma waves is due to electron-ion collisions, and it depends on two quantities. One is the electron density of the corona, where the burst is being generated, and the other is due to the temperature of the corona where the burst is being generated. And so what Hartz did was look at a very large number of type 3 radio bursts, measured the time constant tau of them, and from this information, he was able to infer the temperature of the corona over a large range of distances from the sun. This is a summary of his results, and these were published in 1969. And looking at this graph, you can see the left-hand scale, the frequency scale. This is the frequency of the bursts, and assumed to be also the plasma frequency in the corona where the bursts are generated. Notice the temperature scale at the bottom. These are the temperatures that Hartz inferred from the time constants of the burst, according to standard theory, which is represented by this formula here. And this set of data that you see here, first of all, notice that relatively close to the sun, at 4 solar radii from the sun, the temperature is about 1 million degrees. And much further from the sun, around the orbit of the Earth, 200, I'm sorry, that's not true. Forget that. Further away from the sun, at about 40 solar radii from the sun, you can see the temperatures drop to about 50,000 degrees. So this data of temperature versus distance from the sun fits in nicely with whatever information was available from other sources, which wasn't very much. It was usually either very close to the sun, where the temperature of the corona peaks at about 2 million degrees, or very far from the sun, about 200-odd solar radii, the orbit of the Earth, where satellites measure the temperature of the corona, which is often known there as the solar wind. And so Hartz's data fills in a nice big piece of that great gap between measurements close to the sun and measurements far from the sun in the solar corona. I would say, summarizing, that this was a very clever experiment because the Alouette satellites were launched in order to probe the Earth's ionosphere. But by looking at the AGC voltage of the satellite receiver, Hartz simultaneously probed the temperatures in the solar corona over, as you can see, quite a large range of distances. And moreover, what made this data important was this range of distances from the sun, which solar emissions in this range of distances, or this frequency range, are generally inaccessible by ground-based solar radio observations because the ionosphere blocks these low frequencies from getting down to the ground. I think that about summarizes it. Thank you. You rat. Well, I don't have much time for that, but here, you know, I was very, well, naturally, going into this field of solar radio bursts, I had seen the beautiful photographs that were shown in Australian Journal of Physics from CSIRO of solar radio bursts, the dynamic spectra, which I showed near the beginning of the talk. And so I thought, well, we'll have to produce dynamic spectra from these Alouette satellite records. And that's the setup that was used to do it, which actually is not similar in principle that the setups that are used in most places. I think there's a tape recorder here. I think in this case, the AGC records were on tape and fed into the intensity of an oscilloscope. Where are they? Where is it? Not that one. It's in here somewhere. It just doesn't show up in this slide, but varied the intensity of it. And then it needed a slow horizontal sweep because the satellite Alouette 1 sweep was about 18 seconds long. And this is how you sophisticated way of generating a slow sweep. I think there's an electric motor here turning a rheostat. We did get some primitive dynamic spectra, but my supervisor, Vic Hughes, as some of you probably knew him, said, "Oh," I mean, he just took one look at that setup that I had there and said, "Oh, no, we're not going to do it that way. We want numbers. This has to be done digitally." So he bought what do we call something to read the records anyway. And you just press a button, you put the crosshairs on the trace and press a button, and punch a card with the correct number of the height of the trace on it. And there it is. There's a type 3 solar radio burst, all in numbers. That pleased Hughes no end. And but I always liked the dynamic spectrum representation. So I tricked the printer into, instead of printing a number, it would go, this is one horizontal trace, 18-second horizontal trace of the satellite. And instead of printing the number, it would go over, print this trace over and over again, and until it produced a black spot. And the number of times it went over depended upon the number, the digital number that was represented. And this was fine. I mean, it pleased me. It didn't please Hughes much, I don't think. But this had one flaw. When I first tried to use this program, the printer did go across and print a line over and over again, but something was wrong with my program, and it wouldn't stop, and it printed over and over and over, like the Sorcerer's Apprentice, you know, and finally, the bottom half of the record fell off on the floor, and I surreptitiously rolled it up and stuck out of the computer center.